So good morning, everyone. I want to thank the organizers for giving me this opportunity to share my result with you. This is on purifying noisy quantum states. The results were jointly obtained with Andrew Childs, Honghao Fu, Zhi Li, Ozols, and Vedang Vyas. We sent off a manuscript to the archive a few months ago, and since then we have quite a large number of improvements and extensions. So anyone interested in the topic and want to discuss further or want to study further on the problem, please do not hesitate to contact me, and I can chat with you online about what we have improved on, because they are not on the archive yet. So let me first explain the problem of the quantum state purification. Suppose there is this mixed quantum state given by, on d dimension, given by this density matrix rho delta. It says that with probability 1 minus delta, you get this signal state. It is a pure state psi. This is unknown to you, but this is a signal state that you want to experiment on. For instance, you may want to do quantum computation on this state, or you want to extract some information about this quantum state. With probability delta, you get noise. And for most of this talk, the noisy data is given by the maximally mixed state on d dimension. So this is the matrix I over d. So this is a mixture of the signal and the noise, giving me the noisy density matrix. So the goal is to produce a copy of rho epsilon, similar to what you're given, except the noise epsilon is substantially smaller. It's a lot smaller than delta. You know delta, epsilon, and d, and you can perform perfect computation, quantum computation. So your goal is to make this copy of the less noisy state so that you can do better computation on it. You are given any number of copies that you want, as many as you need to perform the task of the noisy state. So the natural question you may want to ask is, for example, what is the expected number of copies you need to obtain this less noisy rho epsilon? Why there is an expectation here? The reason is simple. A lot of these purification protocols involves measurements. Therefore, it is not deterministic upfront how many copies you need. Sometimes you have better luck, sometimes you have worse luck. So a natural measure of complexity is the average number of copies you need in your protocol. Another question you can ask is, how much quantum memory do I need to perform the purification, and how complex is the circuit for me to do the purification here? So we'll try to address some of these questions in the talk. Before I present my result, I want to share what is already known in the literature about the problem. One of the earliest work was done by Zurek, Eckert, and Machiavello in 1998. Probably a lot of you were not even born at the time. I noticed students are very young. They studied the problem for the qubit case, and they find an optimal expression for the sample complexity as a function of the initial and the final errors. It is rather remarkable that as long as you don't demand zero error in the output, and you have any signal, like as long as delta is not 1, you can do it. So there is no threshold. It can be done. These functions are fairly gentle, reasonable function of epsilon and 1 minus delta, and they can prove that it is optimal. So everything is nice and simple. Even more surprisingly, not only you can have 1 copy, you can have more than 1 copy. You can have roughly n times 1 minus delta copies. These are correlated copies, so they can't be used together. But if you use just one at a time, then they all have roughly the same error. So it's quite a surprise result, I think. There were some extensions by Kell and Werner shortly afterwards on other varieties in the error definitions and so on. And both work identify another interesting problem to relate to state purification. Cloning, which you may have heard of before, is a natural reverse of state purification. There, you are given a small number of relatively noiseless copies of the state, and you want to make many more copies of the state in exchange for having more noise in each copy. So that is the reverse of purification. And in both work, they study cloning along with purification. So let me first present one of the earlier results in this project. It was obtained a long time ago. It was written up in Honghao's master thesis 10 years ago for the qubit case, wherein he finds the sample complexity for the qubit case to be very similar to the qubit case. These two expressions are very similar. Don't be deceived by the 2 versus 3 here. There is the second order term around, so there is no clear understanding which of the 2 expressions is bigger. We do not know whether the qubit case is harder or easier, but they are similar. That's what we know. Likewise, there is no threshold. It has a fairly similar flavor in that it uses the full permutation symmetry and the kind of covariance of the depolarized noise to obtain the result. But to generalize the result to higher dimension turns out to be rather difficult. You can guess. We started around 2014, and we did not actually have a result along this direction for larger dimension. The approach to use weak search sampling, we managed to get the fidelity as a linear program, but there are parts of this linear program that turns out to be a little hard to compute, so we do not actually know the best trade-off between the fidelity or the error and the sample complexity here. Maris is still working on it, so anyone interested in this approach, you can contact him for more discussion. Before I start on the bulk of today's talk, let me also mention that there is a slightly different approach, that you do not demand that you always output the good state that you want, but you allow a very large substantial probability to fail. And this can be phrased as SDP, and there is an older result in 2004 and a more recent result just at the very early this month. But they are very different from the problem that we're discussing, because we want the copy of state always, and we allow the protocol to run longer or shorter. So we have no fixed input to the problem, contrary to this SDP formulation when you have a known input state for the purification. Is there any question before I move on to the main result for the talk?
Maybe I have a quick question. Can you go back to the previous slide?
Mm-hmm.
So in the expression, so you write n plus 1 equals to 102 epsilon and so on. So how am I supposed to understand this? The complexity is given by the right-hand side of the expressions. And what does the n plus 1 represent here?
N is the number of copies of the noisy state you need.
Yes.
And n plus 1 is basically n for large n.
Right.
And so you need roughly delta over epsilon over 1 minus delta square number of copies to suppress the noise from delta to epsilon.
So can we just go back to first slide and see the question again?
Can you hear the question?
It's hard.
Yeah, Han Chen, can you repeat?
Hello, can we go back to the first slide and just see the problem definition again?
Yeah, so Han Chen was asking you to go back to the first slide to see the problem definition.
Okay, and okay, no delta. Okay, so the state size is not known. So I see. Okay, unknown state. Okay, I see. Thank you.
Yeah, he's good now. Okay.
Okay, good.
Any other questions? Okay, I think we can continue. Yeah.
Yeah, thank you for taking the questions for me.
No problem.
So we decide to let go of bang our head to get the optimal fidelity and the sample complexity trade-off. We think good enough is good enough. We do not need to do it the best. So by saying that, we come up with a simpler protocol. So we fix the protocol instead of demanding something being optimal. And we just hope that the protocol is good enough for the purpose. So we propose to use recursive swap tests, which I will describe in detail later. This will allow us to do the purification. And for certain noise regime, it allows us to have an efficient circuit, low memory space, and also, most importantly, allows us to do the analysis. And so let me start with the swap test. The swap test is a circuit that takes two inputs. Each is d dimension. For now, assume that the state on the two system is arbitrary. So tau is the density matrix for a completely arbitrary input on S1 and S2 together. The swap test attaches an ancilla, a qubit ancilla in the plus state, which is just 0 plus 1 renormalized. If your ancilla is in the computational state of 1, then it will swap S1 and S2, and otherwise it will do nothing. Afterwards, there will be a measurement on the ancilla in the computational basis. The outcome A is either plus or minus. Now, it takes a moment to verify, so I may not do it on the spot here. But the whole circuit here requires order log the number of gates if you want to decompose it into 1 and 2 qubit gates. And when D is 2 to the K, it means that you have K qubits. Then the circuit size is linear in the number of qubits that you have. So it's a very small circuit for the problem size. And now what does it do to your state? If the outcome is plus, then it projects your input into the symmetric space of S1 and S2. If the outcome is minus, then it's projected to the anti-symmetric space of S1 and S2. So now, if we start to specialize and run the swap test on product state, so you have a rho here and a sigma here, then the probability to get plus versus minus has a bias. So you have a half on each, but then there is a bias, which is trace of rho times sigma. Now, this bias is large if and only if rho and sigma are both fairly pure and equal to one another. In fact, it is one if and only if rho equals to sigma and they both are pure. So our idea is that if we post-select the outcome of plus, so we reject the outcome, we reject the output when we get the minus outcome, we only take the system when the outcome is plus, then we potentially should post-select the purer, more similar component of rho and sigma. And that should allow us to purify. Furthermore, we only keep S1 and we throw away S2 because later on we want to recursively run this swap test. So we don't want to accidentally take two states that are correlated with one another. So just for hygiene, we don't keep both copies, we keep one out of the two. Now, to specialize further, if rho in fact is equal to sigma, you have rho and rho here. Then condition on the plus outcome, the output state is rho plus rho square, renormalized. It says that the eigenvectors are preserved. The eigenvalues are also changed a little bit. The maximum eigenvalue, if it is non-degenerate, will be increased by the process. The rest, because they are, eventually want to apply it to the deploy state, then the rest will be decreased, but decreased in the same amount. So it preserves the form of the state also. And because the maximum eigenvalue always increase, we know that if we keep recursively running the swap test, we'll eventually get better and better purity of the state. And so let me state the protocol for the recursive use of this swap test. We ask for 2 copies. We send them through a swap test. If it's plus, we keep S1, throw away S2. We do that again. This time I get a minus. Whoops. Throw both away. Everything red in the diagram, I throw away. I ask for 2 more copies. This time I'm lucky. I get the plus. No, now I have 2 copies of the more pure state from these runs. So I can send them through yet another swap test in the hope to get yet another purer copy. So now I want a second copy of this level of purity. So I ask for more pairs of rho data. And in this case, I run down one level, and then I get 2 copies of the first level states. Then I run these 2 through another sort test. If I'm lucky, I get a plus state, then I get a plus outcome, then I get another state here. Now these 2 states are identical. I can again send them through the same sort test. Whoops, this time I get a minus. Everything gets to be thrown away. I have to start again. But the point is that if I keep trying, I keep building these binary trees and keeping the good states, the error, the noise will go down. So let me define some notation here. The basic noise, the delta, that is the noise of the state given to you, we call it delta 0. After 1 round of sort test, the noise of the output is delta 1. After 2 levels of the sort test, we call the noise of the state delta 2 and so on. And the hope is eventually you get to a delta n, a small n, which is smaller than epsilon. Then you can output this state and you're done. So that's the recursive sort test. It's exactly what you think it is. It is the most naive, simple thing you can come up with. Now, there are something very interesting about this test, this recursive test. If we use a streaming model, which means that these pairs of row delta is provided to you on demand. You ask, you take them, but you don't store the rest of them until you ask for them. Then you take the pair in and you have to deal with it. Before that, you don't need to deal with the massive supply of it. It's just sitting in the store. If you have this streaming model, then there is an architecture called the stack-based implementation that requires only n plus 1 qubit plus 1 qubit quantum memory. So what is a stack-based implementation? I look it up on Wikipedia. It is named after a stack of plates. So these are just plates. There's a stack of it. We don't even need to worry how to initialize them because you can push the data up and you can overwrite the data. So the idea is that you ask for 2 copies of row delta at the beginning. You run the sort test here. If it fails, you do nothing. You ask for another 2 copies and you override these 2, the lowest 2. If it passes, then you push the first copy. This is S1, this is S2. You push S1 to the plate above it. And you store row delta 1 up there in the 3rd plate in the diagram. Then you ask for 2 more copies. And if it passes, then you take the 3rd place and push it up. And then you take the 2nd place and push it to the 3rd plate. So by moving things around and pairing them up side by side, you can run the sort test on the 2 identical copies next to one another. If it passes, you push it 1 up. If it fails, you leave it because you're going to override it. Slowly, you will be able to output the row delta n at the very top. And the amount of memory is correct. That is stated there. So it's kind of a cute little result. We can ask other resources required by the test. Each swap test require only order lofty gate, but the number of tests, if you just stare at those trees, it is exponential in the number of iterations. Likewise, the number of leaves here, which is the sample complexity, is also exponential in the number of iterations. So then the question, of course, how many iterations do I need to get from delta to epsilon? So let's take a quick look at the recurrence relation of the delta i's. Remember that we take 2 row delta i's and get a row delta I plus 1. And it is not hard to do, but I'm not going to derive it on the spot here. This is the recurrence relation. The important thing is to rewrite it a little bit and then notice some interesting features here. If delta I itself is small, then the recurrence is very insensitive to the dimension because the dimension is appearing in 1 over d multiplied to delta I. So it doesn't matter very much for large dimension. They all behave very similarly as long as the noise is small enough. And we'll see how small is small enough later. The other interesting thing is that if the noise is small enough, then you ignore this term, and roughly speaking, delta I plus 1 is delta I divided by 2. So you halve the noise every iteration when delta I is small enough.